everything in experimental science. So we're going to start with the problem that I set you yesterday about how to, with Bayesian methods, how you can infer something from a really small amount of data. And as I said, sometimes in cosmology we would like to have 1,000 universes, but we only have one. So the question is, can you do any inference with a very small amount of data? So the problem that I set you was to try to work out the slope of the number counts of a population, given only one source. Can you work out the slope? Did anybody have a go at this problem? I guess probably not, but let's go through it now. Let me just remind you of the problem. So pay attention to this problem, because I will come back to it later when we do some more advanced concepts in the course. On the last day that we're giving lectures, then I will come back to this in the context of Bayesian hierarchical models. So we'll build on this problem. So if you pay attention now, then it will be worth it later. So just to remind you what the problem is, we measure some fluxes, and we have an experiment that can measure fluxes down to a certain minimum level, which is S0. And we measure one source, one flux, without any error, so we're not concerned with any errors on the measurement here. And we measure it precisely with a value of twice the minimum. Okay? And the model that we want to constrain is a model where the slope of the number counts is alpha minus alpha. So the number per unit flux range is s to the minus alpha. Goes like s to the minus alpha. So this was used many, many years ago, this sort of argument, to argue against the steady state theory and in favor of the Big Bang theory. In fact, it was quite complicated in those days. So can you tell anything? Well, let's go through this in a Bayesian way and see how we can, what we can learn. So I said that the distribution was proportional to s to the minus alpha. So the first point is to notice that you have to normalize this distribution properly. And that is because the number that you expect depends on at any flux, and it does depend on the slope. So we have a distribution which, in terms of log S and log n, is a power law with a slope of minus alpha. And if we interpret this as a probability distribution, then if we change the slope of alpha, then we have to change the normalization as well, so that it integrates to 1. And that turns out to be important, because the normalization depends on alpha. And as you can see here, there's a factor out the front, which is alpha minus 1. So given that what we're going to calculate is a posterior for alpha, it's a function of alpha, then the normalization out the front becomes important. So how do we do this? So this is an example of a continuous probability density. So there's one or two conceptual issues to just to think of. So this is a useful example for that reason. If we want to turn this probability density, so P of S is a probability density, it's not a probability. This means that in a small range of delta S around S, then the probability is P of S times delta S. So P of S times delta S is a probability. P of S itself is a probability density. So the expected number of sources, if you in a small range of fluxes, will just be given by P of S delta S times the number of sources that you observe. Okay, so that would be the expected number. So what we do is to choose delta S so small, so effectively we take the distribution of sources and divide it into a large number of small ranges, each of which has a width of delta S. So you don't actually have to do this in practice, because you can essentially use the result that I'll come to at the end if you're dealing with a continuous density, a continuous distribution. but this is a construction that allows you to get to the probability. So if we choose delta S to be so small that none of these bins has more than one source in it. So let's say we have a certain number of sources, we'll take one in the end, but let's say we have 4, then we choose these bins to be small enough so that the number of sources in any one bin is either 0 or 1. And we can always do that just by making delta S small enough. Now within each of the bins, then the probability of getting 0 or 1 is just a Poisson distribution, which Licha talked about earlier today. So we know those probabilities. We know the probability of getting 0. So the probability of getting n is the expected number to the n e to the minus lambda divided by n factorial. So if we've chosen these bins so small that there is essentially no chance of having 2 or more sources in the bin, then the only probabilities that we need to be worried about are the probability of having an empty bin, which is just e to the minus lambda, and the probability of having a source in the bin, which is just lambda e to the minus lambda. So we just look at n of 0, 1. Okay, so if these sources are independent, then if we want the probability of getting that particular set of filled bins, we just multiply the probabilities together. So that's the probability, multiply all the probabilities of the empty cells, the empty bins, each of which has a probability of e to the minus lambda, and then the probability of the filled bins, each filled bin has a probability of lambda e to the minus lambda. These lambdas depend on the bin number, which I haven't shown here, but so we just multiply the probabilities together like that. And then if we take the limit of small bins so that essentially lambda goes to 0, goes towards 0, if we make the sizes of the bins infinitesimally small, then the probability of getting the set of values that we've observed, this thing here on the left, is that all of these probabilities are essentially 1 for the empty cells as lambda approaches 0, so to leading order this is just 1, so this term goes away, and we just get left with this product, and here the e to the minus lambda is again approaches unity, so we just take the lambda for each of the sources. Okay, so that gives us the probability for any continuous distribution of objects, of getting the data set given the parameters of the model. I haven't put the conditional on alpha here. Conditional on alpha and n, I guess, would be the correct thing. Okay, so we just need to multiply the probabilities of the lambdas, and you'll see that the lambdas depend on P of S, but they also depend on n and delta S. The delta S is not important because that's not a function of alpha. So if we observe n sources, so n is a fixed number, delta S is some arbitrary number that doesn't depend on alpha, then the dependence on alpha of this whole thing is only through the P of S term. Okay, so the other parts change the constant of proportionality, but it's not important there, because they don't depend on alpha. Is that clear? So although we've done this construction where we've made these small bins, in fact the width of the bin doesn't matter in the end as long as it's small enough that you only have 0 or 1 source in the bin. So this is just quite a very general expression that if you have a histogram or a distribution of sources, then you don't actually need to. So another way to do this would be to bin the sources and make a histogram of the data. But you don't need to do that. You can just work with the fluxes that you have. If you bin the data, one approach that you might first think of is, all right, let me take my data, I'll make a histogram of it, and then I'll work with these numbers in the histograms. And you could do an analysis like that, based on binning the data, explicitly binning the data into a histogram. But you lose information if you do that. You don't need to do it at all. You can just work with any continuous field like this. Okay, so this is the thing we need to look at. This is if we take a model which is this power law distribution, then the likelihood, and hence the posterior, if we assume a uniform prior on alpha, then the posterior for alpha will just be the product of these P of S's at the observed fluxes. Okay, so that is the result. That's the result of the experiment. That encompasses all of the information that we've learned, having made the observations of the fluxes. Okay. And you see why the normalization, normalizing the probability in this case is important, because we have an alpha dependence that comes from that. Okay, so we can explore this. I mean, actually just simply blotting out that is the result of the experiment, but let's just explore it a little bit. We can find the most likely value of alpha by maximizing this likelihood. It's also the maximum of the posterior. If we take a uniform prior, then the maximum likelihood value of alpha is also sometimes called the MAP, M-A-P, the maximum a posteriori value of alpha. So it's the most probable one. So it turns out to, in many cases, to be more convenient to maximize the logarithm of the probability rather than the probability itself. So let's take logs first. Take log of this expression and just get a sum of these things, plus an irrelevant constant. And then we can differentiate that with respect to alpha to find the maximum likelihood value. So you can do that trivially. Just differentiate, and then you get an expression for the maximum likelihood value of alpha must satisfy, given by this. And then you just rearrange it to find alpha. So it turns out to be this thing here. If you've got little n sources, I think I made it big N before, so apologies for changing notation. For little n sources, then the maximum likelihood value of alpha is 1 plus n over the sum of log of Si over the minimum detectable flux. Okay, so for the case that I gave you, which was to say we have one source, which has a flux of twice S0, then you can do this perfectly well with one source. 0 is no good, but 1 is fine. And if you work that out, then you find that the maximum likelihood value for alpha in that case is 2.44. Okay, so, but really, as I say, the real output of the experiment is not just the maximum likelihood point. So this is the posterior probability of alpha against alpha. Probably you can't read the numbers along here. It's quite skewed because we only have one source. If we did this with 1,000 sources, we'd have something which would no doubt look very Gaussian. So that is what we've learned from the experiment. So you might like to try that. You can, if you want to do this experiment, you can write a small Python code that generates some values of S given a particular alpha, and see if your posterior encompasses the true value. So the maximum likelihood value won't be the value that you put in, no doubt, but it should be somewhere near the P, near enough to be consistent with it. It's maybe worth just pausing to think, how can we work out the slope of number counts given one source? How does that work? It works because we have that extra information of the minimum detectable flux. So basically, if this is S0, then we do have some information even from one source, because if the source happens to be very close to S0, then the likelihood is that the slope of the number counts is very steep. But if the value of S that we had was much bigger than S0, then the likelihood is that the slope of the number counts has to be flat. So it's the fact that we know about S0 as well as the flux of the source that we observe that allows us to say something about how steep the number counts are. Okay, is that clear? Is there anybody got any questions on this problem? Anything that's not understandable? Okay, so that's a general technique for any source of data which is drawn from a continuous distribution. Very rarely do you actually have to bin the data into, explicitly into groups. It just loses information. If you want to do this experiment, just to generate some fluxes from a distribution, then I thought I'd just say something about generating random numbers from distributions. We'll cover this, or we'll need to cover this, with all of the sampling methods. So most of you are doing projects that involve sampling of some description, and actually drawing random samples from distributions is not a trivial exercise, particularly in many dimensions. But let me show you some of the techniques, one of the techniques that we can use. So one thing we can use is to transform the data. If you have a way to generate random numbers, let's say uniformly from 0 to 1, and I guess every computer language probably has something for doing that, then you can use those random numbers very often to generate distributions, numbers from different distributions. So we can use the conservation of probability that if we make a transformation from x to y, then p of x dx is p of y dy. So if we want to draw some numbers from a distribution specified by p of y, like the s to the minus alpha that we have here, then if we draw some numbers from a uniform distribution, p of x, so that p of x is a constant, then provided that we choose dx by dy appropriately, we might be able to generate some numbers from a different distribution. So from a power law, so if we want to draw some numbers from s to the minus alpha, then if we draw x uniformly from 0 to 1, and an exercise for you would be to work out what the transformation is from s to x, such that if p of x is uniform, so this is constant, to make p of y to the minus alpha, what do you need for the transformation x to y? And clearly it's the dx by dy term which is going to give you what you need. So you should be able to show very easily that the transformation that you need is that s is s0 times x to the minus 1 over alpha minus 1. Alpha has to be more than 1.
Is it p of s equals alpha?
P of s here. So this is proportional to, it's actually a Greek alpha because my computer doesn't give me a proportional to. So but to get the you have to get the normalization correct as well, but you should be able to show, I don't know if you can read that, that's x to the minus 1 over alpha minus 1. Just as an aside, you can't use this trick to generate Gaussian random numbers, but there is another trick due to Box and Fuller, where if you draw two random numbers from 0 to 1, x1 and x2, then if you construct this quantity, then the distribution of this quantity is a Gaussian distribution from with zero mean and unit variance. So if you ever needed to generate Gaussian random numbers and you had somehow lost any part, NumPy or any other libraries, I mean, any random number generator will have a way to do this, but if you wanted to do it yourself, or had to do it yourself, then this is a way to do it. Okay, so that was a relatively simple example of using the Bayesian method to infer the slope. I want to digress for a moment and talk about the central limit theorem. As I say, this underpins all of experimental science, really, and it's the reason why we can do so well with science. It's also the reason why when you go to your funding agencies, you always demand more data. I want more observing time. And the reason for that is basically due to the central limit theorem. So, as I'm sure you know, the central limit theorem says that if you take the average of a lot of identically distributed random variables, then in the limit of the large numbers, then subject to some relatively mild conditions, then the average will tend to a Gaussian distribution with a variance which decreases as the number of samples increases. That's extremely useful because it means that we don't necessarily need to know what the distribution of the individual objects is. If we average enough of them, we can assume it's Gaussian. And very often in cosmology, we don't know the distribution of individual objects, so this averaging can be very useful. So let me go through the proof of it, because it's such a central piece of statistics. Let's start by saying that we have a random variable z, and whose probability distribution is p of z. Then the probability of the value of z being larger than some value z1 is just the integral of p of z above z1. So what I'm going to do here is to work out the probability of the sum of two random variables, and then we'll generalize it to many. So if we let z be x plus y, x and y have identical distributions. Sometimes in statistics this is called IID, independent, identically distributed variables. Then the probability of the sum being larger than z1 is given by the joint probability of p of x and y integrated over the region of xy space that has x plus y larger than z1. So that restricts us to the green part of this going off to infinity. So we need to integrate the joint probability distribution over the region where x plus y is larger than z1. So if we write that down as a double integral, we let y go from minus infinity to infinity, but at a given value of y, then then x only goes from z1 minus y to infinity, so just to the right of the point. If they're independent, then we can factorize the joint probability distribution p of x and y into p of x, into p of x times p of y. So at this point I've actually kept it general, so these probability distributions could be different at this point, so I've put an x subscript on here. We'll in fact only apply this where these two probability distributions are the same. For now it's general. Okay, so there I've just written the equation from the last slide up again. We can do a change of variable here, back from changing x to back to little z, which is just x plus y. So x in here becomes z minus y, and the integral becomes the integral. I've actually reversed the order here for reasons which will become apparent in a moment. But we integrate p of x evaluated at z minus y times p of y. Alright, so by writing down this cumulative probability distribution, the probability of being larger than z1, then we can infer what the probability density function for p of z is. Because by definition, the cumulative probability distribution is the integral from z1 to infinity. I think I've made a mistake with one of these limits, I think. Sorry, this lower limit here should be z1, not minus infinity. So if you then just compare these two, then you see that the p of z is just this inner integral. And that tells us what the distribution of the sum of two random variables is. And you see that it's a convolution. So it's a convolution of the probability distribution of x and the probability distribution of y. So as you know, if you have convolutions, then if we were to take the Fourier transform of these distributions, then we would multiply the Fourier transforms. So Leacher introduced the generating function, or sometimes called the characteristic function, which is just the Fourier transform, the inverse Fourier transform, depending on your convention, of the probability distribution. So if we have a convolution for Z, then it's a product in the Fourier space. So the characteristic function for Z is just the product of the characteristic functions for X and Y. Okay, so if the observations are from the same distribution, then these characteristic functions are the same. So we'll just call it phi. And if we make n independent observations, then we can just generalize this to say that the characteristic function for Z is just the nth power of the characteristic function for X. Okay? So that in itself can be quite a useful result. If you're averaging over, well, this is actually the sum of variables. We'll come to averaging in a moment. If you want to know the probability distribution of the sum of variables, then using the characteristic functions is a very useful and easy way to get the distribution. Okay, so this leads us towards the central limit theorem, which is to look to see what happens when n tends to infinity in this case. So, just to remind you what Leacher said this morning, that if we take the characteristic function of the p of x, then if we expand the exponential as a power series, then what that tells us is that the characteristic function is 1 plus I times the expectation value of x times k, plus another term that depends on the expectation value of x, and so on. So let's consider not the sum of variables, but let's divide it by the square root of n. Now, this is not the average, clearly, but you'll see why, bear with me, why this is a convenient thing to do. The characteristic function for this sum is, well, it's almost the product of the individual characteristic functions, but because of the appearance of root n in here, you'll see that if I replace the x's by x over root n, and the x squared by x squared over n, so we just reintroduce the power of n for each term. What we can do is then associate the root n here, not with the x, but with the k. So we can write this as 1 plus I times the expectation value of x times k over root 2, and this one is k squared over 2, and so on. So we just attach the root n here that appears in this equation, attach it to the k's. So we end up with the effect of the root n is to change the argument of the characteristic function by the root n term. So let's make this a bit specific and say, just for simplicity, let's assume that the expectation value is 0 without loss of generality, and let's let the variance be sigma squared. Then, if we just take the first 3 terms in this expansion, ignore everything else, second term is 0 by the assumption. So the characteristic function is just 1 minus a half sigma squared k squared, and because of the root n here, then we need to divide by n. So there's some extra terms here to the right which I've ignored. Okay, but then if we have this expression and we let n tend to infinity, then it's well known that this tends to a Gaussian distribution in the limit. So this ends up being e to the minus this term without the n, so e to the minus. So 1 minus x over n to the power n tends to e to the minus x in the limit. So this tends to this Gaussian form. Okay. So that tells us that in the limit of large n, then the characteristic function is a Gaussian in k-space. And if we want to get the probability distribution, then we invert the transform, and as you know, the inverse of a Gaussian is a Gaussian. So P of this quantity, big X, is this, just inverting the Gaussian in the transform. So now we can just, by change of variable, we can work out the probability distribution for the average. So X bar, the average is X over root n, so this becomes 1 over n. And again, just by the rules of probability, P of X bar dx bar is P of X dx. So in translating from one to the other, the only difference is a factor of root n. So what does that tell us? Well, it tells us that the probability distribution for the mean of a large number of observations that are identically distributed and independent is a Gaussian with zero mean, because this was the case that we considered, and with a variance which is given by the variance of the individual observations divided by n. Okay, so this is a Gaussian width, which is sigma x over root n. So what does that tell us? It tells us that the average of a very large number n identically distributed random variables, which are independent, I've missed that out here, that's also important. The average of many independent identically distributed random variables tends to a Gaussian with a variance given by the variance of the variables divided by n. So it's an amazing theory, it's incredibly useful. As I said, if you do collect any experimental data, you don't need to know what the distribution is, because if you take enough of the data and you average it, then you know what the statistical properties of the average are. The other thing that helps us in science a lot, of course, is that the errors go down as you make more observations. So if you want to get this distribution narrower and narrower, then all you do is to collect more data. Okay, just to give you a word of warning, that is that there are some distributions for which this does not apply. Peter already mentioned the Cauchy distribution. This is a simple example. 1 over 1 plus x squared with a normalization 1 over pi. So that's a distribution that looks like this. This doesn't obey the central limit theorem. Can anybody think why? Doesn't have a variance, that's right. So if you multiply this by x squared and integrate over x, then it diverges. So it either doesn't have a variance or has infinite variance depending on your taste. So it doesn't obey this. Okay, so now I'm going to get you to do some work. I'm going to give you a problem which is a classic problem in Bayesian inference. It was devised by Steve Jarl, who was my internal PhD examiner, who was a committed Bayesian. He gave this to first-year undergraduates at Cambridge many, many years ago, and so I remember this. I've known this for a long time, and when I was preparing for this course, I thought I'll just have another look at it, and I thought there'll definitely be a twist in this. There'll be some interesting feature of this problem. Steve is such a committed Bayesian that there will be some reason why he chose this particular problem. And I thought the reason for it would be to make frequentists look bad. Okay, and it's absolutely right, because what we'll do is you'll do the Bayesian calculation. If you finish it quickly, then I'll ask you to do a frequentist calculation. If not, I'll do the frequentist calculation and I'll show how utterly it fails, whereas the Bayesian method works extremely nicely. So let's set up the problem. We have a lighthouse which is situated off the shore of a straight shore line. It has some unknown coordinates which are x0 and y0. So y0 is the distance away from the shore. x0 is its location along the shoreline. And it sends a series of flashes in random directions. So it's rotating light. And the flashes arrive, half of the flashes arrive on the shoreline, the others go out into the sea. So here's the first one, the second one over here, the third one over here. And the data that are collected are simply the positions of the flashes where they hit the shoreline. So no information is recorded about the direction, or indeed the intensity of the light that lands here. The only information is just this value of x, this value, and this value. Okay, so your task is to, using a Bayesian approach, find the posterior distribution of the position of the lighthouse x naught, y naught, given a set of positions xi. Okay, and I'll give you a little while to do it because it's an instructive exercise. If you have a solution, come and write it up on the board, and there'll be a prize. I don't know what. The first correct answer. A bit more light, it's a bit dark. You want a bit more light in the room? Yeah? Is it possible to turn the lights up a little bit for a while?